In this podcast, we're going to apply the definitions whereby the derivative of sine of x with respect to x is equal to the cosine of x, along with the derivative of cosine of x with respect to x is negative sine x, along with all of the rules that we've used when differentiating polynomial functions and rational functions to what we're doing here in this unit on trigonometry. So recognize that with the first example here, uh, with the equation y equals sine 3x, notice that there is an inner portion, which we refer to in trigonometry as the argument um, of the sine. You might think of it as 3x as being 3 times the angle and then taking the sine of that. It really is also the inner function in this case. We can denote that as being u. And if we're going to express the inner function in terms of u, what that means is that here on the outside, we have an outer function, which we'll denote as the sine of u. Now, with that being said, we can definitely differentiate these expressions. So the first one, we'll find the derivative of y with respect to u, and that's the cosine of u. We will also find the derivative of u with respect to x, and that is equal to 3. Now, based on what we had learned earlier with regards to the chain rule, okay, we know that the derivative of the expression y with respect to x is going to be cos u multiplied by 3. That is to say, we take du by dx and we multiply it by dy by du. Okay, notice that we can cancel the du's, hence the reason why we end up with dy by dx. So let's insert the expressions we've come up with. That would be 3 multiplied by the cosine of u. Now that's not necessarily dy by dx, okay? What we do need to do is this is dy by du, given the variable we have here. So if we want to express it in terms of x, what we must do is then say to ourselves, the derivative of y with respect to x really occurs such that u is equal to 3x. This is what we began with in terms of our substitution. So we'll return and replace u by 3x. And there we have our derivative correct and done correctly. We'll run through 2 or 3 more just to give you a broad range of examples so that you can successfully apply them when solving problems. This one here looks somewhat more busy, but again, we'll use the chain rule along with some substitution methods. We'll begin by identifying our inner and outer functions. So cosine of the argument, this would be the inner function. We'll denote that as u, and then the outer function, including the constant multiplier of minus 3, we'll take that as minus 3 cos u. So what we'll do is we're going to determine the derivative of y with respect to u. So that would end up being minus 3 multiplied by minus of sine u. And recall, the reason that we can say that is recall that the derivative of cosine of x with respect to x is minus sine x. So that's the property that we're using. Let's tidy this up a bit more by getting rid of our negatives. Distribute the negatives and we have positive 3 sine u. Now, In terms of the inner embedded function, 2 pi x, so the derivative of u with respect to x would be simply 2 pi. Okay, so 2 pi is the constant multiplier of x. So had that just been 2x, we would have said that the derivative is 2. But because of pi being multiplied by 2, the derivative must be 2 pi. So in order to finish this question off, what we need to do is to determine dy by dx when u, which we have above, is 2 pi x. So let's begin with that, and we'll substitute in the value of u into our expression. So let's take on du by dx, that's 2 pi. We'll multiply that by 3 sine. Now do you recall what u is equal to? 2 pi x. So at the end of the day, we have nothing more than, let's distribute here, 6 pi multiplied by the sine of 2 pi x. Our third example grows a little bit more in terms of its complexity. Here we have the cosine of sine x, but cubed. So cos cubed sine x. What you might find helpful here is we can again use a substitution method, but sometimes it does get tedious in having to write a lot of the notation. We might try to do something differently here. What we could consider, given that it is in Lagrange notation, we could maybe walk away from trying to do the substitution. We're going to re-express this. This is also equivalent to cosine of sine x, but all cubed. So I think we can get a sense of appreciation for how the power rule will also be important in terms of the chain rule. Okay? So let's go ahead and see if we can differentiate this particular function. I'm just going to clone that expression. And what we're going to do is we're going to try to find g prime at x. So I had cloned that. I was going to flip back to Leibniz notation. I have a tendency for that, but I'll try not to. So let's start out here, g prime at x. First thing we're going to do is we're going to apply the power rule. So what you see color-coded in red is, let's begin with this. So we would end up with 3 being multiplied by this inner function cosine of sine x. And that would be to the power of 2. Okay? Now that that's been taken care of, the derivative of the outer function, we then need to look to the inside. Okay? And what you can see on the inside is the cosine of sine x. So what we're going to do is apply the chain rule again. And this is an interesting problem in that what was color-coded red, that outer function is a cubic function. If you look inside, we actually have 2 more functions. We have a sine x being embedded as an inner function inside of a cosine function. And then the cosine function is being embedded inside of a cubic function. So we really have a lot of embedded functions here. So we can see how the chain rule is going to be not used only once, but it's going to be used twice. So the first time we applied the power rule, chain rule is coming out at us right here, right now, with what you see color-coded in green. So we're going to go ahead and find the derivative of cosine, and we know that is minus sine. And the argument was sine x. Last but not least, we apply the chain rule again, or finish the chain rule, and notice that there is a function embedded within the cosine. So the derivative of sine x is cos x. So there we have correctly right, correctly determine the derivative of g at x. The last thing we might consider doing is rearranging a few terms just in order to give it a different look. So we could bring together a few items. Let's consider the 3. Let's consider the negative, bringing that together. So let's begin doing that. So we'd have 3 minus 3. Also, let's bring in perhaps the single term here of degree 1. So let's bring in the cosine. Let's follow it up. We'll increase in terms of degree. Let's go with this term here. So that would be 3 cos x multiplied by the sine. I'm going to keep the brackets just to differentiate between each of these terms. It also helps us to see in terms of an order of operations what has to occur first if we were to apply this. And last but not least, it's more of a standard procedure not to leave the answer written in this notation, but rather in this form here. So let's bring that 2 back in here, and we'll finish it off with cosine squared of sine x. Okay. Last but not least, let's try this one out. Maybe not quite as daunting a task as before, but we are going to see the product rule being used as well as the power rule for differentiating expressions. So I do want you to see that there are 2 terms being used here. We have 3x squared being multiplied by a second term, sine of x. So as far as the product rule is concerned, just recall that if this function, call it y, equals 2 functions u times v, then the derivative of y with respect to whatever the independent variable is. Here it's not necessarily indicated, so we'll just go with Lagrange notation. So you would take the derivative of the first, multiply it by the second, and then add on the first times the derivative of the second. So using this rule, let's go ahead and do that. Let's take the derivative of the first term, 3x squared. So f prime at x will be 6x. We'll multiply that by the second term, which is the sine of x, to which we're going to add on. Okay, here we are adding, and then we'll finish with u v prime. So u is 3x squared being multiplied by the derivative of sine x, which in this case is the cosine of x. Okay, and there you have it. Really not much of a need to go any further with this. These terms cannot be added. The only thing that anybody could do with this right now would be to consider factoring an x along with a 3 out of the expression. So we could pull out a 3x and have 2 sine x plus x cos x. Okay, as a final factored form. So there you have it. The derivatives of expressions, functions involving sines, cosines. Next step is for you to apply these and to solve tangent point problems, as well as to begin applying these to situations where we're modeling using real world phenomena.